The fourth type of force that we will encounter is tension, which has to do with ropes, chains, maybe even someone's arm pulling on something. You can use a capital T or F sub T to represent that tension force. The key things to know about tension forces is that they always are directed away from the object and right along with the rope, right parallel to the rope. So you end up drawing them right on top of a string or a chain or whatever it happens to be. And that the tension force actually pulls in two directions at the same time. And so we'll have to kind of see how that looks. We'll look at an example here in a minute. The rope, or if a rope or a number of ropes are tied together at a knot, we should also recognize that there's no reason that the different ropes pull with the same amount of tension. So we should assume that they are all different. Let's take a look at an example where we see tension forces in action. So here we have a setup where some ropes are being used to suspend a mass down here, and also to keep this situation along with friction in place. So let's take a look at some of the forces that are acting. Let's first look at this knot. So when you have this place where three forces are coming together, each force needs to be considered a different value. So I've labeled these FT1, FT2, and FT3. And we would use some trigonometry and so forth to relate these to each other. So the other thing then to understand about tension forces is they do pull on either side of the rope. Right now, this force body diagram, or free body diagram, this is talking all about the pulls on that knot, on that little spot there. If I'm interested in what happens to this block over here, then I would instead be thinking about the tension force pulling to the right instead of pulling to the left. But notice that these two forces marked yellow, they would have the same magnitude, they are just in opposite directions. And so that's something useful to be aware of. Just kind of finishing off this block over here, the reason it's not moving is because the frictional force points to the left, and that exactly equals the tension force, causing this object to be in equilibrium. There would also be a normal force up, perpendicular again to that surface, and a gravitational force down. Again, gravity always points down in our pictures.